Primitives in Rust are a variety of different kinds of data that can be represented in a variable in the Rust programming language. We have a whole bunch of varieties of variables, like numbers, letters, and we call those scalar types. These scalar types are sort of like sort of a single unit or a span of memory that can represent data that is accessible and you can manipulate and reuse in your Rust programming language. So the varieties we have are numbers, like integers, and we have things called signed and unsigned integers, which is confusing. Why do they should just call it positive and negative, right? So a signed integer is just a whole number that can be positive and negative. The different numbers associated with these i's, like I8, I16, I32, I64, these represent how big the number can get. So like I8, the number's maximum size is 255. I16 is like 65,550 something. Wait, I want to see I'm guessing here. So with I16, it means 16 bits. How many bits in binary can represent a number? So if you turn on every single bit, your maximum number is 65,535. And then going one step further, you can have there's no reason why you couldn't have 17 bits. And if you had 17 bits, you would have a maximum number of 131,000. Though I guess it's uncommon. If you wanted, you could have it, but Rust gives you these default options that sort of double each time. So a 32-bit number, that would be, I'm going to flip all these bits here really quick. I know it's like somewhere around 4 billion, isn't it? It's like 4.29 billion. And that would be a 32-bit number. And so if you know that you're going to be needing a number that's going to be below... Oh, wait. There's a catch. With a signed integer, you're actually going to leverage one of those bits for if it's a negative. So you can sort of span below 0. And one of those bits will be whether the number is positive or negative. So your maximum signed integer is going to be 2.14 million. And it can be negative, but your smallest number could be negative 2.14 billion. So that's something to watch out for. Often, if you know that you're not going to need anything to be represented in a negative number, you can just use unsigned integers. So that way you get to take full advantage of the maximum capacity of that integer. So you could get full value. Basically, you're dividing the maximum value in half when you're using signed integers. And then if you want even a bigger number, you can go with a 64-bit, and I'm clicking all the bits on, and I'm looking at the maximum possible value here. And it is a number that I can't pronounce. I can't pronounce this number, so you probably will only ever really need a 64-bit number, even if if you're using signed or unsigned, it's going to be a very big number. When we're representing this number as a fraction, that's what we call as a floating point number. That's where you'll have a decimal somewhere in the middle of the number. And it's not any much different than how data is stored in bits compared to these integers. It's just that we now have a fraction representation where the data can be split into, instead of whole numbers, it's full numbers. But it's still the same bits, right? You're still leveraging the same number of bits on the computer. We're just sort of we're representing them differently, but it's the same data. It's the same physical data. And there is a float 32 and a float 64. So you can have higher precision by using float 64 because you'll have more bits and more decimal places. We also have char, which is character, which is essentially just a single value, right? It's just a single letter. It says Unicode. So it's probably going to be in the range of U16 or U32, representing a character numerical value, but we can interpolate that as like the letter A. Oh, 4 bytes. Okay. So that will be probably a U32 in this case, right? Because we're going to use a Unicode, 4 bytes. So that means that we can access every possible character ever human written or needed, including emoticons and emojis, right? So we could any symbolic characters used in any language and any alphanumeric characters used in the Latin languages. A character is going to be just one letter. And then we have bool, which is Boolean, which is going to be a true or false, usually just like a 1-bit value, right? 1 bit. So it means it's really tiny. But usually computer systems come in larger chunks, so you might not be able to leverage, you'll be wasting data. but sometimes not, depending on how Boolean's used within the compiler and the programming language. And then we also have a sort of an empty type here, which is an empty tuple, which is basically representing like there's kind of nothing. It's kind of a null. This might be the null. This actually might be Rust's null. Essentially, it's nothing. Despite the value of a unit type being a tuple, it is not considered a compound type because it does not contain multiple values when it's empty like this. Interesting. Rust also provides us a couple of different frames for collecting a variety of variables or primitives. These are two foundational types of compound. They're compound types that allow us to group together a cluster. Our normal variables are scalar types here, like numbers and variables of like floating points and Booleans and characters. And we can put them together in lists. So there's two kinds of lists. These compound types in Rust, we have an array and we have a tuple. Tuple. They're both a list. In Rust with arrays, you'll typically want to sort of bundle together the same kind of thing all together in one list. You can go out of your way to make different types of variables, different types of data structured in an array. If you really want to, though, it's better to do something like that. If you want to have a mixed type of data in a list, you can use a tuple to do that. So you can have like a number, an integer, and then you can also have a Boolean represented in the same group. Whereas with an array, you'll have typically just all numbers or all characters or all Booleans. So these are compound types. And these are the foundational types. Now, obviously, we can go more complicated than this. We can go more complex and have more capabilities. Though now you're adding into the language something that's not foundational to the language. Usually, though, you only really need these things. You don't need to go too much further than these. And so when we're looking at the code that represents the different kinds of variables that Rust gives to us, we have a Boolean, which you can annotate with bool. Though you don't have to have that, you could do just this, and Rust will figure it out. You can have a float with an F64, and then that's represented with a period followed by a number, or no number. I bet you could do it like, maybe. Some languages let you do it like this. Rust might require you to have at least a 0 ending there. Let's try it out. Let's double check. All right. Okay, so it actually works. So if you want to represent your floating number like this, as long as you have a period, Rust is perfectly happy with that. It's a little bit easier to read if you put like a 0 at the end of it, so you kind of see what's going on, but it means the same thing. You even don't need to represent, you don't even see F64. The default, it says here, is going to be F64. So you don't even need to annotate the kind that it's going to be. And if we run, it still works perfectly fine. So this can be a minimal float definition right here. There's also a suffix annotation. What do you know? Okay, hold on a second. Let's try that with the float to see. F60, is it going to like that? I don't know. Let's find out. If it says, okay, maybe it really wants a 0 there now in that case. Let's see. So if you're going to use a suffix annotation where you define the data like this, you need to have a 0 or something that's a number right next to it. Otherwise, it won't like the suffix annotation. So this is pretty neat. I didn't know you could do this. It's really hard to read. What is this? It looks some sort of cryptic 128. What is that number? What is going on here? Yeah, usually you just here we go. An integer, perfect. This is a minimal representation. Rust likes this pattern as well. It can figure out what you mean. The default's going to be I32 when you don't include. This is I32 here. Yeah, you can see here the next line down, default I32, default F64. We don't need the 0. We'll also go over this a little bit later in another video. Talk about mutability in Rust. The ability to mutate data inside of your Rust variables requires extra definitions with the mute. When you're defining your variable, if you want to be able to change the value, you must say mut in front of it, because you can define a variable starting it out with a 12. Ooh, neat. Look at this. Okay, so when we are defining, this is neat that the compiler figured this out. We've got an inferred type here, even though we're assigning it 12, which can be default to I32. It's actually going to give it an I64 because it's going to see that it's a much larger number. But also it's annotated with a suffix. So it's going to I64. Now it's going to be an 128, right? Is that going to work? It might work. Yep. Okay. So it will, the compiler, you don't even have to annotate the type. It's going to automatically, in this case, it's a 128 because I said 128 further down in the line right here. These suffixes are, they're tricky to see. It's very difficult to see that this number is like sort of a little hidden value there. I don't recommend this approach. What happens if we exclude it? Oh, it needs that suffix. Okay. If you don't have that suffix there, it's going to complain. Look at that. I64. Let's try again. Okay, now it's happy. All right. So if you ever run into a situation where you've got a number and it grows beyond the default I32 and you need to assign it and it's immutable, you'll have to add this cryptic suffix at the end. It will let you infer the type. The compiler will be able to infer the type and it won't complain. It won't give you a bunch of errors. This is a tricky one. It's probably better just to, if you know it's going to be a big number, just do this. Just do it like that. Define it up front. And now it's fine. And it's easier to read. We have a little bit more to the picture here. The story gets more complicated. All right, so something that kind of is fair and obvious, when you do define a variable and you say that you can mutate it, you can change the data that's in the variable that's being represented to say 12 to 21. That's perfectly fine. We're happy. We're good to go. If you try to change the type to a Boolean, from an integer to a Boolean, the compiler's going to say, nope, can't do that. And we'll get an error. So we'll see here, I'm going to try that. We expect this value is going to be, in the integer range, an I32 mutable, though we found a Boolean, which is problematic, right? The Rust language is going to help you along the way to say, oh, you probably don't want to do that. And oh, also you can't do that unless you do something called shadowing, which is a whole thing, which it sounds like it's a powerful feature, though I don't know if I like it because we're redefining the same variable name that we had already defined above. We're saying it's an integer. Oh no, just kidding. It's a Boolean now. What's going to happen when we run this, it should just be, yep, no errors. Rust lets you do this? We'll probably jump into this later, but there's a whole thing on shadowing later. Variable shadowing is allowed. Okay, so variable shadowing occurs when a variable is declared within a certain scope, like those curly braces, and it has the same variable name declared in an outer scope, so something above it, somewhere above. This, I think, is okay from a code cleanliness perspective if you are just trying to represent the same state, though it is confusing. It really is, because you're putting two things that are they're the exact same name in proximity to each other, so it's going to be pretty easy to confuse anyone who's reading the code, though it is allowed. This can lead to confusion, as it may be unclear which variable subsequent user is shadowed by the name referred to. Yeah, which depends on the name resolution of the language. So Rust lets you do this. So here's the top scope here. We have v equals 1. Then you can also redefine v, essentially a mutation of v, to be 2. And then you can go even further and multiply that by 2 and print v. So we've done it twice here. We've done 2 shadows. Note that this is Rust. This is some other, this is Lua in this case. It's Lua. It's the same logic in Rust. And then once the scope ends and you print v again, it's going to be the value that it was before, and then you print v again. And so it does allow this nesting. Okay. I mean, it might be better just to, give it a different variable name, specifically because that is a confusion opportunity. We want to be careful with that one. Rust lets you do it, though. Variable shadowing. Just watch out for it because it might happen to you.